Welcome back. Thank you for joining me. This would be the last video on this particular model, which is the hydrolysis of sodium borohydride, right? So you are welcome to this lecture. Now, the last phase of this model is to simulate the regeneration of the feed, which is sodium borohydride, right? So I tried to research about it, but I couldn't get enough information, especially with respect to the reaction itself, right? So now I'll just make use of this particular journal, which is the regeneration of spent sodium borohydride back to sodium borohydride by using high energy ball milling, right? Just to pick out some information. So you have the equation here, right? You have NaBO2, which is sodium metaborate plus magnesium plus 2 moles of hydrogen gas to give you sodium borohydride plus magnesium oxide, right? So I would make use of this. I couldn't find the conversion, right? I couldn't find the conversion of the process or the reaction, and then I couldn't find kinetics about it either. So I guess most of those things are still under research or something. I couldn't really get such data online in my own personal research, but I would still advise you to research more about it, and in case you can find useful information, then you can make use of it, right? So I will be making a lot of assumptions from this point, right? So for this reaction, it says it can work under high pressure 3.1 megapascal, that's 31 bar, and then elevated temperature of 550 degrees Celsius, right? So I'll be making use of these values to simulate the reaction that produces sodium borohydride, right? So now you notice that most of the values I used are from some of these journals, right? So the essence of that is to actually know the process conditions of that particular process, right? Have an idea of what already is existing and what works, right? So it doesn't mean you automatically have to use those values, right? You must not use those values exactly, but they will serve as a basis to whatever you are going to choose eventually, right? So, but in this case, I just want to use them like that, right? I'm just trying to illustrate how you could simulate the process, right? But when you are simulating yours, you can make slight changes to the parameters, and this will help to make your work actually be novel or new, right? Instead of just using the already existing process conditions and all, right? So, but in this case, I will just use them like that. Now, we are going over to the simulation environment. So, we have our sodium metaborate here. Should be somewhere here, right? In this the bottom of this second separator. So we'll be separating the sodium metaborate from the other components present in this stream. So we need a separator here, right? We need a separator here. Sorry about that. Okay, so I should press OK. Yeah, we need a separator here. Then what else do we need? So our reaction is NaBO2 plus 2Mg plus 2 moles of hydrogen. So we need some hydrogen to also be part of this process, right? Now we can make use of some of the hydrogen that was produced in the first reaction, because hydrogen is our target product. We can actually, so you can either make use of part of the hydrogen that was produced, or you can add a new hydrogen stream to the process. Either works. So, but I want to use part of this hydrogen produced, right? Because we are trying to produce the feed to the process, which will eventually still produce more hydrogen. So I will just use the hydrogen, part of the hydrogen produced. So to do that, I will make use of a T, right? An F split called a T in HYSYS. So I'll just click it and then click on it on the flow sheet, right? So this would separate this stream into multiple streams, either 2 or more streams, right? So you can either specify the split or you specify the flow rate, right? F split. So you can either specify the split or you specify the flow rate. But before we do that, we need to connect it to the inlet, which is this. So you double click on it and then you connect it to your split, right? Then the next thing is to go back to the split, and then okay, we still need to specify the outlet also. The outlet will be, we have our hydrogen product, right? What will I name it as? Okay, H2PD. I hope I have not used this before. Okay, then we need another stream. So this one is, let me just name it React H2, right? So this is like the opposite of the mixer, right? So the mixer, you have multiple streams entering and then a single stream leaving, while this one you have a single stream entering and multiple streams leaving. So it's just the opposite of the role of the mixer, right? So we go back to that particular equipment F split to specify the splits of the streams that will be exiting the equipment. So in this case, I'll specify, you can specify at least one of them, or you can specify all of them if you want. So I will specify just one, which is the hydrogen that will be used for this second reaction. And in this case, I want to specify the flow instead of specifying the split. So the flow for me would be, this is an assumption, right? Yeah, 20 kilomole per hour, right? Okay, let's move. Once you have specified at least one of the streams, one of the outlet streams, you are good to go with that. So you can run the simulation, right? Then let's go back to the flow sheet. Okay, so we have specified so this will serve as our overall hydrogen product, while this will be a part of the second process. So we have created hydrogen required for this second reaction. Now we need magnesium and then the sodium metaborate, right? So we are going to make use of a separator to separate sodium metaborate from the other components in this stream, right? So we click on it here and click OK. Then we attach material streams to the top and the bottom. So this is NaBO2, right? Then the bottom, I will just use this. Okay, so we are good. Then we connect the feed to that particular separator, right? So this separator will separate sodium metaborate from the other components. What we need to do now is to open this and then specify the splits, right? So you can either specify splits or you specify flow, whichever one you want to do. You must specify at least one of the splits of or one of the flows of any of these components, right? You can specify more than one, but you must specify at least one, right? So in this case, we want all the sodium metaborate to come out from the top of the outlet. So in the outlet you have the top and then the bottom, right? So for the top, you want to specify sodium metaborate as 1, so that all of the sodium metaborate would leave from the top of the separator, right? Then you click on run, right? So if you check it, B10 stream results, you would see that it is just the sodium metaborate that leaves from the top, right? So no other component is there, right? So we can now continue with our modeling. The next phase of the modeling is to create a stream for magnesium components that will be involved in the reaction. For the magnesium stream, we will make use of atmospheric temperature, which is 25 degrees Celsius, but for our pressure, we'll be using the same pressure as of the other streams, which is 30.2 bar, right? 30.2 bar. Then our feed rate is 20 kilomole per hour, right? 20 kilomole per hour. That's an assumed basis. Then mg is 1. The composition of mg in this stream is 1, right? Then you can run, then continue with your model. So these 3 streams, the magnesium, hydrogen and sodium metaborate, are to be mixed together before they are fed into a reactor, right? So I need a mixer here. Okay, I need a mixer. Now I'll be sending these 3 streams into the mixer. So I double click on it and connect to the mixer. Same with the other 2 streams, right? Then this, right? Then we need an outlet stream for the mixer. We need an outlet stream for the mixer. Mix out. Yes, so we have that. So we have our feed for the reaction, right? Run this. Then we are making use of 550 degrees as the temperature of the feed inlet to the reactor, right? So we have to raise the temperature of this mixer outlet before it is fed into the reactor, right? So we have 550 degrees Celsius. So that is what we will be making use of. So we need a heater. For that, right? Okay. So the heater inlet is the mixer outlet. So we need to add an outlet for the heater. So this is hot feed. Then we connect the mixer outlet. Let's shift this a little. We connect the mixer outlet to the heater. Just double click and connect, right? Then you click on next. If you don't know what to do, just click on next. So it takes you into the heater so that you can specify the heater properly. So temperature is 550 degrees Celsius. Then pressure is the outlet pressure. I'll make use of 30 bar. Outlet pressure, that is the pressure of the outlet, the heater outlet, right? So once you are done specifying your heater, your heat exchanger, you click on run, right? So you can check the stream results, right? So the mixture is at 550 and 30 bar, 550 degrees Celsius and 30 bar. So we have our conditions for the reaction we want to model, right? So we can now simulate the reaction. Now, I said earlier that I did not really find much on this particular reaction, so I will just make use of some assumptions just to illustrate how it can be modeled. So in this modeling, I don't have kinetics for this particular reaction, so I just want to use the stoichiometric reactor, which is RStoic, and then I'll specify a conversion for the process, right? So you bring out your stoichiometric reactor, RStoic, you connect your feed to the reactor, right? You connect your feed to the reactor, then you create a stream, a material stream for the product. You create a stream for the product and you are good. Then you open the reactor, you can specify the conditions and then the reaction that is taking place inside the reactor, right? Unlike the plugged flow, you remember the plugged flow, we had to specify the reaction outside the reactor via the reaction section in the navigation pane, right? This was where we specified the reaction that took place in the plug flow. In the case of this RStoic reactor, you are expected to specify the reaction inside the equipment, inside the reactor, right? So you should take note of that. So for the temperature, it's still the same temperature as the feed, that is 550, and this is 30 bar, right? That's for the specification. Valid phases, I'll leave it as vapor liquid because our feed is a combination of liquid and gas, that is hydrogen. So I'll leave it like that. Let me see. Yeah, I'll leave it as vapor liquid. Then reaction, we specify our reaction, So you click on new, then you add the components and their stoichiometry, right? Then we have Mg, then here we have NaBH4 and magnesium oxide, right? So we now specify their stoichiometry, that's -1, negative for reactants and positive for products, right? You add the negative sign for your reactants and then the positive for products, right? Yes. So now we are almost done with our specification. All you need to specify next is the fractional conversion, right? So in this case, I'll make use of a fractional conversion of 0.5. Now this is an assumption because I could not get information about conversion or kinetics, right? I couldn't get either for this particular reaction, so this is an assumption, right? So if we assume a fractional conversion of 0.5 for NaBO2, for example, right, we are done specifying the stoichiometry reactor. We are done specifying it. You can click on next and then you click on run, right? So the process, the software is doing the calculations, right? You can check your status, and yes, the calculations were completed normally. So you can check your results, go back to the main flow sheet. Then from RStoic we can check the results of the reactor, right? So we are in RStoic now, the stoichiometry reactor. You click on stream results and you can see the calculations that were done by the software. You see the product stream and the feed stream, right? Feed stream is hot feed and product is R1PD, right? So we can check the amount of sodium borohydride that was formed from the process based on the specifications. So you have your mole flow. From here, NaBH4 that was formed is 9.4 kmol per hour, right? Then MgO is 18.9 kmol per hour. So those are our products, NaBH4 and MgO, right? Then what else is here? Okay, we now have the unreacted feed, also unreacted feed components like water is 1.07, then NaBO2 is 9.46, right? So these are this is the composition of the product, the molar flow composition of the product. Then you can also check the mass flow composition as well if you want, right? So we have been able to produce or regenerate the feed, which is NaBH4, right? So we have gone through the whole model from this beginning, which is the hydrolysis of NaBH4. Let me adjust this a little so that you can see it properly. Okay, this is okay. Let's see. Then this. Okay, yes. Then we have this. So this is what we have, right? This is the whole process from the hydrolysis of sodium borohydride, right, that forms hydrogen, and then the reaction of sodium metaborate with magnesium and hydrogen to create the feed, which is sodium borohydride, right? So I will stop here for this particular problem, right? So you can still do more research about the two processes involved in this model so that you can get more accurate results than this, right? So this is just to help you get a little information about modeling this particular process, right? So you must not do exactly what you have seen here. You can just use it as a basis to do your own model, right? Because you always want your model to be novel, right? Novel and unique. So you can use this as a basis for your own model, right? So this is just to try to help you to get foundational knowledge on how to model this particular process, right? So with this, we have come to the end of this series, or the modeling of sodium borohydride, right? I hope you have gained some knowledge from the 3 tutorial videos that were made on this particular topic, right? If you have questions about this, you can drop comments using the comment section. Then you can like this video, share with your friends, subscribe to this channel and then to the main channel as well if you have not done so, so that you can be getting notifications on subsequent tutorials, right? Thank you for joining me. Do have a good day.